Now, this beautiful table is probably something you remember from grade 10 chemistry. That big poster sitting on the wall of every chemistry room in Australia. You're looking at it and you're going, oh no, I didn't do this program to do chemistry. Well, let me tell you, this table, I believe, is one of the most amazing things that human beings have ever been able to create. What this table shows you is basically every ingredient that is required to make every single thing in the entire universe. I cannot emphasize that enough. If I want to create you or I or your dog or the table or even the earth or the sun or the galaxy or the entire universe, these are the ingredients that you need. Nothing more, right? There's 118 of these ingredients, and we actually call these ingredients elements. So there's 118 elements. Now, if I wanted to make a human being from scratch, if I wanted to make you from scratch, I don't need all 118. I actually only need 59 of these ingredients or elements. And in actual fact, 6 of these 59 would allow me to create 99% of you. What are these 6? Well, these 6 are hydrogen, carbon, nitrogen, oxygen, calcium, and phosphorus. Just these 6, I would be able to make 99% of your body weight, which is amazing. Now, I said 59. So what about the other 53 elements? Well, the other 53 elements we only need in very, very, very small quantities. Often we term them trace elements, and some of these include things like sodium, for example. So we only need a little bit of sodium, a little bit of magnesium, a little bit of potassium, a little bit of chlorine, for example. But in actual fact, a couple of important points here is this. Many of these elements don't exist in this neutral form that we see on the periodic table when they're in the body. Now, what do I mean by neutral form? Well, let's take a look. Let's just first start with the very first element on the periodic table, that is hydrogen. Now, if I had one hydrogen atom, now think about that. Atom is another term I'm introducing. Remember, element is the flavor. Atom is the quantity. So for example, hydrogen is an element, but I can have one hydrogen atom or I can have 1,000,000 hydrogen atoms. But the flavor of it is hydrogen. That's the element. Just like chocolate ice cream, that's the element, but a single scoop or 2 scoops or 3 scoops, that's the atom of equivalent. All right? So 118 elements, but many, many atoms. So for example, your body only needs 59 elements to be made, but it's made up of trillions and trillions of atoms. So hopefully I've got that point between atoms and elements highlighted. But again, let's just go back to hydrogen. It's the first element on the periodic table, and you can see it's got that 1 here. Helium is number 2, and it's got 2 here, and lithium is number 3, and so forth. So this number is actually highlighting something. It's highlighting the fact that hydrogen, being number 1, has 1 proton. So that's a positively charged thing sitting in its core. But it also has 1 electron, which is something that flies around the outside of it. Now, an electron is a negatively charged particle. So a hydrogen atom has 1 positively charged particle called a proton and a negatively charged particle called an electron flying around the outside. Now, because there's 1 positive thing and 1 negative thing, they balance each other out, and so it's seen as neutral. So every single one of these elements here are neutral. Helium being 2, this is going to be pretty easy, right? Helium being 2 has 2 protons in its core, and it has 2 electrons flying around the outside of it. So it's neutral. Lithium being 3 has 3 protons and 3 electrons. Beryllium being 4 protons and 4 electrons. I think you get it moving through. Now, what I said to you earlier was that some of these elements, when they exist in the body, they actually have a charge associated with them. Now, think about this. The proton sitting in that core, you can't play around with that. right? That's sitting right in the core. You can't give a proton or take a proton. Because if you do, you actually change the element. Because think about it. Hydrogen is 1 proton. Helium is 2 protons. So if I were to give hydrogen an additional proton, it's no longer hydrogen. It's actually helium. So you can't play around with the protons. You can play around with the electrons, though. So, for example, if I were to take sodium, sodium is number 11. Now, what's an important point here? Well, if sodium is number 11, what if I wanted to, let's write it up here. Sodium is 11. So that means it has 11 protons and 11 electrons. So let's just write 11 positive things right in its core. And the electrons, let's draw them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You got these 11 negative things flying around the outside of sodium. Now it's neutral in this point. But interestingly, some of these trace elements like sodium actually doesn't like having the 11 electrons. Doesn't like the number of electrons. It actually wants to be like something else. Now this brings us to this end of the table up here. This end of the table on the far right hand side. These are what we call the noble gases. Noble gases. That's Nobel. I should learn how to spell. Noble gases. I can't talk and write at the same time. Noble. If something's noble, right, it's proud of itself. It's happy with who it is, and it doesn't want to change. But sodium does. Sodium wants to be like its closest noble gas. So if sodium's 11, what's its closest noble gas? Neon at 10. Now, neon being number 10 has 10 protons and 10 electrons. Sodium has 11 protons, 11 electrons. How could sodium be like neon? Well, you can't change the protons, but you can change the electrons. So neon has 1 less electron than sodium does. So what sodium wants to do when it's in the body is it wants to be like neon, and it throws away one of its electrons, which means it now has 10 electrons and 11 protons. So there's 1 positive charge excess for sodium, which means when sodium's in the body, it's not just written as Na, it's written as Na plus, because there's 1 additional charge, because it's given away its electron. Let's use another example, like chlorine. Chlorine here is number 17. You can't see it because I've covered it with the red circle, but chlorine is number 17. Again, what does that mean? Chlorine has 17 protons in its core and 17 electrons flying around the outside of it. Now, it wants to be like its closest noble gas, which is argon, 18. Now, you can't change the protons, so you can't give it a proton, but you can change the electrons, and you can give it an electron. And so chlorine in the body actually gets given an additional electron and becomes 18 electrons. And it now becomes chloride, not chlorine. But it's left with an overall net negative charge. So chlorine in the body isn't written as Cl, it's written as Cl negative. And that's what we call chloride. Now think about this. Sodium wants to give an electron, chlorine wants to take an electron. What a beautiful relationship. So in the real world, sodium and chlorine live together like this, as salt. And then once it's in the body, it splits apart, and the sodium has lost its electron, and the chlorine has gained its electron, and that's how it exists in the body. This is what we term ions. Ions, as IONS, are charged atoms or elements. They can be positively charged, and in that case we call them a cation, or it can be negatively charged, and in that case we call it an anion. Now you're probably thinking, why is this important to know? It's really important, and you're going to find out why soon.